In the last class, we discussed about heat capacity at constant volume and constant pressure. So, heat capacity at constant volume, we define it as Cv, and we know Cv is del U by del T at constant volume. Okay. And heat capacity at constant pressure, we define it as Cp. Cp is del H by del T at constant pressure. Okay. And we talked about the relationship between Cp and Cv. We know and we derived Cp minus Cv is N times R for ideal gas, where N is the number of moles. Okay, so, for 1 mole, and write Cp minus Cv is R. Okay. So, we discussed this thing in the last lecture. Okay. So, as we discussed just now, so del H by del T at constant pressure gives Cp. Okay. So, if we take the dt other side and if we do the integration, so and Cp usually function of Cp and Cv both usually function of temperature. So, we do it like that, and if we put the limit, we get like that. So, what we get? We get H2 minus H1 is if Cp is independent of temperature, or if Cp is constant, is independent of temperature, or Cp is constant, then we can write del H, that is nothing but H2 minus H1 is Cp times del T, that we are aware of. Okay. So, next we will just briefly discuss what is Kirchhoff equation, okay, or Kirchhoff's law. Okay. It says the delta H so this is Kirchhoff's law. So, derivation we are not going to discuss now, you are all studied this thing, okay, where you know delta Cp represents the difference of the heat capacities of the individual products and reactants at temperature T. So, also this is Kirchhoff's law. You all studied this. Okay. Now, we will move to limitations of first law of thermodynamics. Okay. So, limitations. So, there are some thermodynamic phenomena which cannot be explained by first law of thermodynamics. Okay. Suppose, okay, so we have one bulb here which is filled with bromine gas, and there is a stopcock there. Okay, this is initial state. If we remove the stopcock, we get what we get? We get bromine gas molecules will occupy both the bulbs. Okay, so this is our final state. So this is experiment 1. Consider one more experiment like this. So you have bromine gas in one container and you have nitrogen gas in another container. And if you remove the stopcock, they will mix with each other. So, in both the bulbs, you get mixture of bromine and nitrogen. So, they will mix. So, this is initial state and this is final state. Okay. This is experiment 2. And for both these experiments, delta U is 0 and delta H is 0. So, from first law of thermodynamics, we get the concept of internal energy and enthalpy, and for both the experiments, delta U change in internal energy and delta H change in enthalpy 0 equals to 0. Okay. So, these two processes cannot be explained from first law of thermodynamics. Okay. So, what is happening here? Okay. So, if we examine or if we examine the above processes from a molecular point of view, we see that each process involves an increase in disorder or randomness of the system. So, if we see the experiments carefully again, initially we had bromine gas here in one bulb, another bulb was vacuum, and if we remove the stopcock, this is the stopcock. If we remove the stopcock, bromine gas will spread. Okay. So, the randomness means for each bromine molecule, okay, so both the bulbs are now available to move around. Okay. Similarly, here for bromine and nitrogen case, for experiment 2, if we remove the stopcock, the bromine gas will have access to other bulb. Okay. Similarly, for nitrogen gas molecules, they will have access to occupy the other bulb. Okay. So, randomness and disorderedness increases. So, why it is important? For the processes where energy is not a prime factor, then we need to see the randomness or disorderedness of the system. Okay. Now, in order to quantify or to have quantitative measurements to quantify the disorderedness, or randomness, we need to have a function or we need to have a function or a state function rather, because state function has advantage over any other function, because state function, the property of state function depends only on the state of the system. So, we need to have a state function. Okay. So, we will discuss this thing later also, okay? And actually it gives the concept of entropy. And we define entropy by S. Okay. So, entropy E is nothing but disorderedness or randomness of a system. So, if you remember correctly, we have so far discussed or we have rather proved that U is a state function, U or internal energy is a state function, W or work done is a path function. Okay. What about Q? Okay. So, heat Q is a path function. We have not proved it yet. Okay. So, today we will prove it that Q is a path function. Okay. So, consider a reversible process. Okay. So, from first law of thermodynamics we know du is del Q plus del W. Since the process is reversible, we just in the subscript we mention this is reversible process. Okay. So, we know du is nothing but Cv times dt, we already discussed. So, we can further simplify the equation like this. Okay. Or we can write del Q reversible, we rearrange the things. For ideal gas, because for ideal gas we can write P is inertia by V. Okay. So, we get del q reversible equals to Cv times dt minus n, not minus, rather plus nRT by V. This is the equation we have arrived so far. Now, Cv times dt we can write like this, okay, because this is perfect differential. Or rather this is du. So, we can write like this. Okay. Now, what about the other term? So, we cannot write nRT by V dV like this, because T, absolute temperature T, depends on V, depends on volume V. So, we cannot do like that. So, who is troubling us? Troubling us is T. So, if we divide both sides of the of this equation del q reversible by T, del q reversible equals to Cv dt plus nRT by V dV. If we divide this equation by T, then our problem will solve. Okay. So, if we do it, now if you see this equation del q reversible by T equals to Cv dt by T plus nRV by dV. So, each term in the right hand side is a perfect differential, okay, which says that del q reversible by T, this term is perfect differential. So, what we have obtained so far? We have obtained that del q reversible is not a perfect differential, which says that q is not a state function. Okay, but del q reversible by T is a perfect differential. So, del q reversible by T, this is a state function. And we know del q reversible by T is nothing but ds, okay, that we have studied. So, in a single shot we proved that q is not a state function, q is a path function, as well as we proved that entropy is a state function. Okay. So, we have proved that entropy is a state function. We can prove entropy is a state function in another manner. Okay. So, entropy is a state function, we will prove in different way in a PV diagram. We will prove it. We will prove it in a PV diagram. So, you consider the PV diagram like this. So, P1, V1 and T1 our initial state. So, P1, V1, T1 initial state. And P2, V2, T1 our final state. So, we can reach from the initial state P1, V1, T1 to a final state P2, V2, T1 through path A. If we say this is path A like this, path A, or we can first go to a point is P3, V2, T2 and then we go from here. So, this is path B and path C. Okay. So, path A is reversible process. So, reversible isothermal expansion. So, reversible isothermal temperature is constant here, initial state, in the initial state temperature was T1 and in the final state also temperature is T1. So, this the process is isothermal one, volume increases from V1 to V2. So, this is expansion process. What about path B? Path B, okay, path B is a reversible adiabatic expansion. So, path B is an adiabatic process and this is expansion process because volume again increases from V1 to V2. And what about path C? So, path C is path C is nothing but reversible heating at constant volume. Okay, so, there is no volume change, but the pressure increases from P3 to P2. So, if you want to keep the volume constant, but if you want to increase the pressure, you need to increase the temperature. Okay, so the process is reversible heating at constant volume. Okay, so what we get so far? Okay, so we get from this diagram and the information we have so far, we get del Q, process is reversible one and path is B is 0 because it is adiabatic process. For adiabatic process, there is no heat change. So, since the process is adiabatic one, so for path B there is no heat change. Okay. For path C, del W reversible is 0 because no PV work. There is no PV work, no volume change there. Okay. So, there is no volume change for path C. Okay. So, du for path C is nothing but del Q reversible of path C, and this is nothing but Cv T dt, right. What we need to prove? We need to prove delta S for path A. We need to prove S is state function. In order to have S state function, you need to prove that okay, that the entropy change for path A has to be equal to the entropy change for path B plus entropy change for path C, because entropy is a state function, is not a path function. So, since the initial state and the final states are fixed, so entropy change for path A has to be equal to entropy change of path B plus entropy change of path C. Now, what about path A? Okay. So, for path A, del Q reversible A by T is nothing but entropy change for path A. Okay. And for path A, du for path A is 0, because the process is isothermal one, and we have considered ideal gas. Okay. Since there is no temperature change for path A, so there is no internal energy change for path A. So, it gives us del Q reversible for path A is nothing but minus del W reversible for path A, or plus P dV. Okay. And what is P? dV is A naught T by V dV for ideal gas. So, we get dSA is N R by V dV. Okay. So, if we do the integration, we get delta SA is N R ln. Okay. Final volume is V2, initial volume is V1. Okay. So, this is the entropy change for path A. Okay. Now, what is the entropy change for path B? For path B, delta S is 0, because there is no heat change. This is adiabatic process. Okay. What about for path C? For path C, delta S C okay, because if you go back and check it, okay. So, for path C, del Q reversible equals to Cv dt. Okay. Now, for adiabatic process, del Q is 0, we know. Okay. So, it says du is nothing but del W reversible, if the process is reversible one. Okay. So, for reversible process. Okay. So, it gives us Cvt dt is minus net T by d dV, and if temperature changes from T1 to T2, it gives you some V1 to V2. So, we get Cv times T2 minus T1 equals to nRT ln V1 by V2. Here we considered Cv is constant. We consider Cv is constant. Cv does not change with temperature. Cv is a constant term. Then only you can take Cv out. Okay. So, what we get? We get Cv times T2 minus T1 equals to nRT ln V1 by V2. And what we get? So for path C, delta S. So for path C, we have delta S is CV ln T1 by T2. Okay. So basically here you do one thing here. So you take T this side and okay. So you take okay. So you do it in another way rather. Okay. So you write this one as CV ln T2 by T1. Okay. So you take T other side and then do the integration. Okay. Now we know that CV ln T2 by T1 equals to nR ln V1 by V2. So this one we can write nR ln V2 by V1. Okay. So what we get? We get delta SA is nothing but delta SB plus delta SC. Okay. So this is nothing but your delta SA. Okay. And delta SB is 0. Okay. So it says that S is a state function, because we arrived at the final point P2 V2 T1 from initial point P1 V1 T1 in two different manners. One is via path A, another is a combination of path B and C, and in both cases we get same entropy change. Okay. So it says S is a state function. Okay. So next we will discuss, we will move to second law of thermodynamics. So there are several statements, but we will consider once, we will discuss one statement today. Okay. This one statement is the entropy of an isolated system increases as a result of a spontaneous process. So one statement is the entropy of an isolated system increases as a result of a spontaneous process. Okay. So we will consider how we will prove it. Okay. So we will try to prove it. Okay. So what we consider? We consider one system, big system like this. Okay. In that container we have a wall. This is rigid. We consider one rigid heat conducting wall. Okay, so we consider a big container which has two compartments. We say this is compartment A and this is compartment B. Okay, and these two compartments are separated by a rigid heat conducting wall, and temperature of this compartment is, we say, TA, and volume of this compartment is VA, and if we say the temperature of this compartment is TB and volume of this compartment is VB, okay, and the entire system is isolated from the surroundings, okay. So the entire thing is isolated from surroundings. So the entire thing is isolated from surroundings. Now compartment A and compartment B, they are in equilibrium with themselves, means compartment A is in equilibrium with itself and compartment B is in equilibrium with itself, but they are not in equilibrium with each other, okay. So we know when there is a temperature change, then temperature changes spontaneously from, or heat goes spontaneously from higher temperature to lower temperature, okay. So and since these two compartments are separated by a rigid heat conducting wall, so heat can be transferred from one compartment to another compartment, but volume cannot be changed, okay. So since the whole system is isolated, so O UA plus UB is constant. Internal energy of compartment A plus internal energy of compartment B is constant, okay, and VA is constant, there is no volume change, and VB is constant, because a rigid wall, they are separated by a rigid wall, okay. Now what is entropy change, okay. So of compartment A, D is, if the process is reversible one, we can write it like this, okay, and entropy change for compartment B is like this, okay. Now since del W equals to 0, no work done, so del Q nothing but this, okay, and del Q reversible or compartment B is this, okay. So we know, so we can write dSA is dUA by dA, and dSB is dUB by, okay. So total entropy change if we say ds is nothing but dSA plus dSB. So if you substitute the value of dSA and dSB here, we get but again we know UA plus UB is constant. So it says dUA is nothing but minus dUB. Okay, so we get ds is 1 by Tb minus 1 by Ta times dUB. If you substitute dUA by minus dUB, we get this. Okay, so we arrived one equation which says ds is 1 by Tb minus 1 by Ta times dUB. Now, we will have or we can have three different cases. So, case 1, Tb is greater than Ta. So, the temperature of compartment B is higher than the temperature of compartment A. In that case, dUB is negative, right? Okay, so, if in that case ds is greater than 0, because if you substitute if you for this condition Tb is greater than Ta and dUB is negative, ds is greater than 0. So, total entropy change is 0. Now, case 2, Tb is less than Ta. Okay. If the temperature of compartment B is lower than the temperature of compartment A, in that case dUB is greater than 0. Okay. So, we get again ds greater than 0. And case 3 is Tb equals to Ta. And in this case ds is 0. Okay, so what we observed here? We observed if there is a temperature difference between the compartments, then entropy increases. Okay, and the whole thing is isolated from the surroundings. So, there is no contribution of the surroundings to the system. Okay, so, entropy change is positive, means the process is spontaneous one. So, the heat passes through the wall from one compartment to another compartment spontaneously if there is a temperature difference between the compartments. If there is no temperature difference between the compartments, ds is 0. There is no net entropy change for this process. Okay. So, we get, if we plot schematically as how entropy changes with time. So, if we plot entropy versus time, okay, so we get here spontaneous change, spontaneous increase in entropy, and once it reaches equilibrium, then there is no entropy change, and this is ds greater than 0. So, this is your spontaneous, this is the spontaneous process. Okay, spontaneous process, and this is equilibrium. Okay. So, at equilibrium there is no entropy change, okay, of the system here, because we consider isolated system. Okay, so, ds equals to 0 when system reaches equilibrium for this isolated system, and ds keep on increasing till it reaches equilibrium. Okay, and this is this point we can say is max. Okay. So, maximum entropy. Okay. Once it reaches maximum entropy, then it reaches equilibrium.